All right, so the second speaker is Bowen Wang. He's also from Australia, from the University of Sydney. So Bowen received his Bachelor of Science and Master of Science in Electrical Engineering from the Harbin Institute of Technology in China in 2015 and 17 respectively. Since 2019, he is a PhD student at the University of Sydney with Professor Verbic. His PhD research topic is about inertia support and resiliency enhancement for low voltage distribution network with prosumers installed by PV battery systems, where he investigates novel control strategy for PV battery system based on grid farming techniques and active disturbance rejection control. So thank you, Bowen. I would ask you to share your screen.
Okay, you see the screen.
Perfect. Great. Thank you very much. The
okay, thank you. Yours. Thank you, Fabrizio. Hello, everyone. Good morning, good afternoon, and good evening. Actually, we are in a different time zone, right? My name is Bowen, and I'm from the University of Sydney. I'm coming here today to present my paper entitled Enhanced Battery Controller for Inertia Support in Residential Microgrid, based on the active disturbance rejection control. And in this paper, I'm gonna present the work in 4 aspects. First, I will introduce the background and the motivation, and then I will introduce the basic scenario about the grid forming converter based on the battery. And then I'm gonna say something about the enhanced grid forming control converter with the active disturbance rejection control. And I'm gonna say ADRC for short. And finally, to conclude, I will also say something about the future research. So for the background and the motivation, we are going to focus on the influence on the power system inertia by the increasing penetration of the renewables. As we know, most renewables, such like the wind and the solars, are connected to the grid through the power electronics devices. So they do not provide any inertial response. In a conventional power system like this, inertia comes from the kinetic energy stored in the rotor, and it serves as an immediate source of energy. However, in the power systems dominated by the inverter interface generations, a high rate of change of frequency will be resulted by the generations with no inertial response. So this phenomenon can also be illustrated by the dynamic frequency response of the power system. In conventional power system, the initial response is the first stage following a disturbance, holding the frequency by releasing the energy stored in the rotor. And this response is followed by the primary, secondary, and tertiary control. Comparatively, the frequency response by the converter-based generations, which is highlighted here, experience a much faster primary control, but the problem is the first instance after disturbance, which used to be in the period of the inertial response, cannot be covered by these renewables. So it results in a larger rate of change of frequency. So to find a potential solution, let's assume a system with N generators. The energy stored in the rotor can be expressed in this form. So when the disturbance causes a frequency drop, the energy difference in the rotor will be this guy. So we can see a larger inertia will help to make the frequency difference very small. But in comparison, when some of the generators are replaced by the renewables like this, the system inertia is reduced, which means the frequency drop will be large. So in this case, if we can use an energy storage to contribute to this kind of power difference, it will equivalently provide the extra inertia for the system. To achieve a lower rate of change of frequency, this power should be provided as immediately as possible. So we are considering to use energy storage to offer this inertia. And the good news is that consumers are increasingly investing in the PV battery systems. As a result, it offers a possibility to use batteries as inertia providers. So now the question becomes how to control the converter. We know there are mainly two kind of control strategy for converters. The first one is the grid following control, and the second one is the grid forming control. For the grid following, we know it acts as the controlled current source, which measure the frequency and stay synchronous with the grid. So this kind of phase-locked loop, which measures the frequency, will result a time delay. So that means the power cannot be provided immediately. In comparison, the grid forming converters serves as the voltage sources and provide the standard grid voltage reference. It means, and we know, we know the voltage source responds naturally to the load change. So it provides the genuine inertia. In this case, we are considering to use the grid forming converter to provide genuine inertia to the system. And in this paper, we are using the matching control, which reveals a link between the DC voltage and the output frequency. So we can regulate the frequency output by regulating the DC voltage. And we can also put droop characteristic to the control of the converter. So this figure shows the structure in which matching control is implemented into the battery. And the matching part, which mimics the synchronous generator, is applied in the converter. And the droop control here, which is introduced to the current voltage droop control, is applied in the bidirectional DC-DC converter. So to test the validity of this structure, we are using a residential microgrid. And in this simulation case, we use a diesel generator, which serves as the backup generator. And the primary control of the diesel generator is disabled. And then we use two identical battery grid forming converter, and a PV interface is controlled in the grid following mode. So let's have a look at the result of the power flow. We can see the PV arrays generates a constant power, which reaches its maximum power point. And at 8 seconds, the load changed slightly, which resulted in a power imbalance. And the power from the batteries increased rapidly, experiencing a faster inertial response than the diesel generator. But we can see it also has a shorter duration because the dominant inertial response is conducted by the diesel generator. And after that, the battery primary frequency control is activated, resulting in a steady increase of the power to compensate for the frequency deviation, and the power of the diesel generator returns to the original value. If we have a look at the DC link voltage, we can see the difference between the grid forming control and the grid following control. Observe that the DC link voltage of the PV array is constant during the load change, while the batteries experienced a slight voltage drop due to the energy being released for the frequency support. Then this figure shows the result of the frequency. We can see the frequency stays stable here and then experienced a sudden drop. And then the frequency quickly recovers back. And then it is followed by a steady transition to the post-disturbance level due to the action of the droop control. So according to these figures, we know the grid forming converter based on batteries can serve as inertia providers. The amount of the inertia depends on the rapidity of the power compensation. So a faster power compensation contributes to a larger inertia. So in the next session, we are going to focus on the fast power response. And in this case, we consider to use the active disturbance rejection control to replace the to serve as the current regulator here. The active disturbance rejection control has the essential part, which is called extended state observer. And the advantage of this controller is that it doesn't need the mathematical model of the system. It only needs to know two things. The first one is the system order, and the second one is the output. By the system order, applying the state observer theory, we can design the extended state observer. And by measuring the output, the disturbance of the system can be observed as an extended state variable. And then we feed this disturbance forward as a control input. This disturbance will be rejected automatically. So in ADRC theory, it regards all factors that matter as a total disturbance. It can be an external disturbance or an internal error. It doesn't matter. We don't need to know what it is. We just want to reject it. So this controller can be applied into the battery control. And also, we augment the ADIC controller with an adaptive parameter updating part here, which adjusts the control parameters automatically. Based on the active disturbance rejection control, the current regulator can be designed in this form as the, here. So by applying the ADRC controller, we can compare the results by using traditional PI controller and ADRC controller. And in these figures, we can see ADRC controllers helps get a relatively low rate of change of frequency. And more details for this part can be found in this paper. Finally, to conclude, I would like to say the battery, when it is modeled in the grid forming mode, can serve as a potential inertia provider, and it provides genuine inertia instead of the kind of synthetic inertia provided by the fast frequency response. And the ADRC regulator contributes to a faster response, helps the battery to contribute to more inertia to the grid. And for some future research, we can consider a more realistic battery model, because we know the battery response is very important for this kind of inertia support. So we are going to focus on the response time of the battery and make it more practical in the application. Okay, thank you for your listening, and I'm ready for questions. Thanks.
Okay, thank you, Bowen, for being perfectly in time. So we now welcome questions from the audience. I see that at the current stage there are no questions yet. Maybe I will use this time to ask you it's a sort of general question. So I've seen that you are currently considering a microgrid, which is like a true microgrid in the sense that is even isolated. It's not connected to a public grid. And of course, I mean, this makes also things a bit more challenging from the technical perspective, because you don't have the coupling between active and reactive power. So, well, the question is, well, two questions. One is, why did you choose this case study? In the sense that whether like my isolated microgrid especially are very much considered for rural electrification. I was just wondering whether maybe like in Australia, this is considering as a as a mainstream approach for future applications? And second, the second question is how do you think how do you think that this controller can be extended also to large interconnected systems? Thank you.
For the first question, actually we are using the residential microgrid as a study case, because in Australia, as I said in the motivation, Australia has an increasing investment on the PV battery systems, and we already have these PV battery systems. So why not using them to provide more services? Then that is a basic scenario in Australian network. So we can just take the residential microgrid as a case to see if PV battery system can provide inertia for a small scale system, and if it can, we can make it in a more general case for a larger power system. But in that case, maybe the battery should have a larger capacity or more power density, something like that. So that's what I mentioned in the future research, that we are going to focus on a more realistic battery. That is for the first question. And for the second one, the ADRC controller is a controller which can help get a faster response. So in this case, we just put it into the current control loop of the battery. But in a more general case, it can replace a lot of controllers based on the era, just like the PI controllers.
Mm-hmm. So it could
replace
potentially.
That has more potential.
Yeah, it can replace like actual controllers in power converters. I see. All right. In the meanwhile, we also have 2 questions, as far as I can see at least, from the audience. So maybe you might want to read them and answer them. Mm-hmm. Is that okay, or do you want me to read them for you?
The first one is about the parameter. Actually,
yeah. So maybe we will, for the benefit of the audience and for the recording, we are going to read them. So Rahul Gupta is asking how the controller gains are determined, and if they are robust to disturbances in the systems, and if the control strategy requires to be recomputed in case of new bus PV systems. All right, thank you.
Okay. For the ADRC controller, it has several main gains. The first one is the gain of the extended state observer, and these gains can be selected based on the state observer theory. And in my paper, I have included several papers explaining how to select the parameter of the ADRC controller. And the other one is the gain of the output. For the output gain, it has a lot of ways to select this parameter. It is a kind of robust parameter. So in this case, the only condition for the parameter is that it should be positive. It should be positive, which is consistent with the system we are going to control. And more literally, I have included some references in this paper explaining how to select these parameters.
Okay, thank you very much, Bowen. So there is another question that it will be also our last one. It is from Martin R. Martin is asking, as the ADRC control is used for current regulation, it seems that the controller has to act within very short time. Have you analyzed the computation of the ADRC controller to validate that it can run in real time?
Sorry, we haven't analyzed the computation time of the ADRC controller. In this case, we just compare the ADRC controller with the PI controller, which is a traditional controller. And this simulation is based on the MATLAB Simulink. So if maybe in the future, we can implement this controller and this system into EMT simulation platform, such as PSCAD or RSCAD, to test it in real time. But I think my opinion is that the ADRC controller, when it is implemented in real time, should be selected more carefully about the parameter. That is my opinion.
All right, okay. Okay, so no more questions, and I think also our time is done here. Thank you very much, Bowen,
Okay.
once again for a very interesting presentation. And we now move to the next speaker,